Hello everyone, my name is Matt Poliszczuk, and in this video I will be going over the MEXT Undergraduate 2015 Math B exam. So I'll solve and explain every question. Also, please note that this is part of a series, and in the Math B 2019 video, I give a bit of extra helpful info at the start. But to save time, I'm just going to go right into the questions in this video. So first is question 1, which says, if the equation log base 10 of a of x times log base 10 of b of x plus 1 is equal to 0, with a is greater than 0, b is equal to 0 constants, has a solution x is greater than 0, it follows that b over a is greater than or equal to blank, or blank is greater than or equal to b over a, which is greater than blank. So for this, you need to know the basic log rules. Also, I'm not writing it in my notes here just to save time and space, but all of these logs are in base 10, as the question gives. So to start, what we can do is use the log addition rule to split log a of x into log a plus log x. And we can do the same thing with log b of x. And so now we have these two logs multiplied together. And so then we can, multiply all this out. And what you'll notice is that we actually end up with a quadratic in terms of log x, right? So we have, in this first term, we just have, in this first term, we don't have log x at all. In these two terms, we're multiplying by log x, and in this term we're multiplying by log x squared. So to make it a bit more obvious, I will let log x equal to z. And so what you will see here is that once we do that and we combine like terms, we have this quadratic right here. So we have z squared plus z times log ab plus log a times log b plus 1 is equal to 0. So if we wanted to solve for z, then we could use the quadratic formula like this. But the question doesn't ask for a specific solution. It only asks for the range of values that would give a solution. So for that, we just need to consider this square root. For there to be real solutions to this quadratic, the stuff inside of this square root must be greater than or equal to 0, because you can't find the square root of a negative number. So that just means we just need b squared minus 4ac, which is also known as the discriminant of the quadratic, and I was taught that the symbol for the discriminant is this triangle. And that has to be greater than or equal to 0. So let's plug in the values for a, b, and c, and then expand. So I'm not going to go over every single step here, but basically what you'll see is, so we plug these values in, we expand a little. Also, I did I combined these logs here earlier, but then I realized that I have to split them up anyways, so that step wasn't necessary, but not a big deal. I did move this negative 4 to the other side, so it just becomes that all of this is greater than or equal to 4. Once we expand this log a plus log b squared, you'll notice that we get plus 2 log a log b from that, but we also got negative 4 log a log b from expanding this term over here. And so when we combine that, we end up with log a squared minus 2 log a log b plus log b squared, and hopefully you can recognize that is just the expanded form of log a minus log b squared. And that's greater than or equal to 4, which means that the absolute value of log a minus log b is greater than or equal to 2. So that means we have two possibilities. It's either log a minus log b is greater than or equal to 2, or log b minus log a is greater than or equal to 2. So let's start with the first possibility. So what I did first is I combined the two logs using the log subtraction rule. So we have log a over b is greater than or equal to 2. Then if you take both of these as an exponent of 10, you get that a over b is greater than or equal to 10 to the power of 2, which is just 100. So we have a over b is greater than or equal to 100. And if you're wondering how I did that, I just combined these two rules over here. So first, a to the power of log base a of b is just equal to b. That's one of the log rules, and it's pretty important. So I think they never actually taught this rule to me, or if they did, we never actually really applied it. But if you aren't familiar with this one, definitely make sure to memorize it for the exam. It does come up kind of often. And also, of course, we have if a is equal to b, then c to the power of a is equal to c to the power of b. So here, I took up both of these. I've raised 10 to the power of these things, which because log a over b is greater than or equal to 2, that means 10 to the power of that is greater than or equal to 10 to the power of that. And then here we have 10 to the power of log base 10, so that just becomes a over b. Of course, the question asks for b over a, so now we have to rearrange this a little bit. And definitely be careful here. When I was doing this, I kept making mistakes until I actually went and did every single step very carefully. Maybe that's not a problem for you, but just in case, you should definitely try to be careful here. But anyways, what we end up with is that 1 over 100 is greater than or equal to b over a. And also, here's the thing. The question says that a is greater than 0 and b is greater than 0. Therefore, it kind of goes without saying that b over a must be greater than 0, right? If this is a positive term and this is also a positive term, then this fraction has to be a positive term. And so we found both of these bounds. We have 1 over 100 is greater than or equal to b over a, and b over a is greater than or equal to 0. So that's two parts of the answer to this question. So now let's check the second option, which was log b minus log a is greater than or equal to 2. So once again, I combined the two logs using the subtraction rule. And then again, I did that thing where I took both of these and took 10 to the power of them. And so we end up with b over a is greater than or equal to 100. So this time we don't need to rearrange the fraction. We already have it in the form that we need. And so that is the final part of the answer to this question. So next is question 2, which says, if cosine theta is equal to the square root of 1 over 2 plus 1 over 2 times the square root of 2, and sine theta is equal to negative the square root of 1 over 2 minus 1 over 2 times the square root of 2, with 0 is less than or equal to theta is less than 2 pi, it follows that 2 theta is equal to blank times pi. So for this question, you need to know the half angle identity, which looks like this right here for sine and cosine. In general, the common identities like the half angle, double angle, Pythagorean, and some identities, you should probably memorize. But if you know this one right here, then you can answer this question. Also, the reason why it's plus minus here is because you determine if it's positive or negative from what quadrant the angle is in. So in our case, in this question, we can see that the cosine given is positive and the sine is negative. So that means that our angle theta must be in the fourth quadrant, because this is the only quadrant where cosine of theta will be positive and sine of theta will be negative. So next, what you can notice is that the expressions of cosine and sine that the question gives are very similar to the half angle identities. So in our identities, and I'll specifically be looking at the cosine one here, but if you look at the sine one, you'll get the same results. We have theta over 2 here on the left side, and then just theta, and then just theta right here on the right side. So that means for our expression, or the expression given in the question, where the left side is theta, right? Cosine theta is equal to something. That means that the right side must be 2 times theta, right? So we have cosine theta here, and this is the same as a half angle identity, only in the half angle you start with theta over 2 and you have theta on the right side. Here we're starting with theta, and so we have 2 theta on the right side. And of course cosine of theta is just equal to square root of 1 over 2 plus 1 over 2 times the square root of 2. That's just given in the question, right? And so what you'll notice is that these two expressions, the one that's given in the question and the one that we got from the half angle formula, they're exactly the same except for these two fractions, right? This fraction and this fraction look different, but everything else looks exactly the same, which means, just, by logic, that must mean that this fraction, cosine 2 theta over 2, must be equal to 1 over 2 times the square root of 2. So if we know that, then we can rearrange for a little, and we get, we multiply both sides by 2. We get that cosine 2 theta is equal to 1 over the square root of 2. And then if we use, the special triangle, hopefully you should be able to just recognize this, because this is one of the the special common angles, pi over 4, pi over 3, and pi over 6. You'll see that 2 theta is equal to pi over 4, and then if we divide both sides, that means that theta is equal to pi over 8. But remember before, we found that theta must be in the fourth quadrant. That means that actually our theta is not equal to pi over 8, it is equal to 15 pi over 8. And here you can see this on the unit circle to make it a bit more clear, right? This inside angle right here is pi over 8, which means that the actual angle, if you go around the whole circle, is 15 pi over 8. And so we have our theta is equal to 15 pi over 8, then that means that 2 theta is equal to 15 pi over 4, and that is the answer to this question. So next is question 3, which says, if y equals to log base 2 of x plus the square root of x squared plus 1, then 2 to the power y minus 2 to the power of negative y is equal to blank times x. So for this, you need to know the basic log rules. You also need to know how to rationalize a fraction that has a square root in the denominator. And if you don't know what that means, don't worry, I'll explain it as I go through this question. So to start, we can find that if y equals to, this whole log in base 2, then that means that, that means that 2 to the power of y just equals to this stuff inside of the log, right? Because if we have y equals to this, we take 2 to the power of y, we take 2 to the power of this whole log, and we just end up with what's inside the log. And that's using the same rule that we used in an earlier question, which is that, if you have a to the power of log base a of b, that's just equal to b. And so we know that, so now we know that 2y is equal to this. For 2 to the negative y, we start by doing the same thing, right? 2 to the negative y is just equal to 1 over 2 to the power of y. And we just found what 2 to the power of y is, so we have this here. Now, next what we're going to do here is use a trick to rationalize the denominator, which has a square root. So if you've done a derivatives course, you're probably familiar with this method. But basically, if we have a square root term plus or minus another term, like we do right here, then what you can do is multiply both the numerator and the denominator with the same two terms, except with the sign between them switched. So here we started with x plus the square root of x squared plus 1, and now we're going to multiply both the numerator and the denominator with x minus the square root of x squared plus 1. And of course, since we're multiplying the numerator and the denominator by the same thing, we're not actually changing the term. This still is the same answer. We're just doing this and to rearrange the term a little bit, make it easier to work with. So what that does is it makes this denominator equal to the difference between two squares, right? Because we have x plus this square root, and then we have x minus this square root, and those two things are multiplied by each other. So hopefully you should be able to recognize that that is just the same as x squared minus the square root squared. And so if we do that, of course we have a square root squared, so that just goes away. So now our denominator is just x squared minus 1. Of course, x squared minus x squared, those cancel out. And so our denominator is just minus 1. And so that just means that we take the numerator, multiply by negative 1, and we have that 2 to the power of negative y is equal to the square root of x squared plus 1 minus x. So now the question asks us for what 2 to the power of y minus 2 to the power of negative y is equal to. So we found earlier what 2 to the power of y is equal to. We just found what 2 to the power of negative y is equal to. So if we plug those into our expression, we have x plus the square root minus the square root minus x. So we have plus the square root and minus the square root, so those cancel out. And so we end up with just that 2y minus 2 to the negative y is equal to 2x, and that is the answer to this question. So next is question 4, which says the function f of x is equal to log base 2 of log base 3 of log base 2 of log base 3 of log base 2 of x has the interval x is greater than blank as its maximum domain on real numbers. So to answer this question, you just need to keep a few basic properties of logs in mind. First, the log of 1 is equal to 0, and this is regardless of what the base is. Any base log of 1 will always equal to 0. Secondly, the log of x is undefined when x is less than or equal to 0. So in other words, you can only take a log of a positive number. And finally, the log of base a of a is equal to 1. So if you keep these three rules in mind, then you're able to answer this question. So in my opinion, the easiest way to answer this question is to start from the outside and work your way in. So firstly, we have the log base 2 of all that other stuff inside the brackets, which I will just call a. And for this log to be defined, a must be greater than 0, right? Because because this rule earlier, log of x is undefined when x is less than or equal to 0, meaning for this log to be defined, a has to be greater than 0. So next we're going to add in the second log. So now we have log base 2 of log base 3 of b. And this log base 3 of b is just what we defined as a earlier. So our a has to be greater than 0, which means that b over here has to be greater than 1 because the thing is log 1 is equal to 0. So log of anything greater than 1 will be greater than 0. And we need this to be greater than 0 as we established previously. So then we just do the same thing. Now we add the third log. So we have log base 2 of log base 3 of log base 2 of c. Log base 2 of c is just the same as what we defined as b. And so if b has to be greater than 1, then that means c has to be greater than 2, since we previously established that log base a of a is equal to 1. So if we need this to be greater than 1, then we need c to be greater than 2, since this is a log in base 2. So then we move on to the next log, log base 2 of log base 3 of log base 2 of log base 3 of d. And log base 3 of d is of course equal to c. We establish that c must be greater than 2, and since this is a log in base 3, that means that d must be greater than 3 to the power of 2, which means that d must be greater than 9. Finally, we add in log base 2 of x to all this, which is equal to d. And so that means log base 2 of x must be greater than 9, which means that x must be greater than 2 to the power of 9, which is equal to 512. And so that is the answer to this question. X must be greater than 512. And if you can't solve 2 to the power of 9, that's not a big deal. You can just break it up into two smaller things, like 2 to the power of 4 times 2 to the power of 5, which hopefully you should be able to figure out on your own. And then you can just multiply these together, like on paper. If you just do like 16 times 32 and work it all out. So hopefully you can figure that out on your own. So next is question 5, which says the total number of subtractions that result in 11111 remaining after a 4-digit number has been subtracted from a 5-digit number and the digits 1 through 9 have all been used is blank. So this is a pretty interesting question. It doesn't really require you to know anything specific except what a factorial is and what one of its main uses is, specifically how to use a factorial to find the different possible combinations of a set of items. And I guess I'll quickly define what that is now. If you have, X amount of items and you want to figure out how many different ways you can arrange those items, the number of total possible arrangements is equal to X factorial. And factorial is just equal to, 1 times 2 times 3 times 4 times 5, so on until X. So if, for example, we had, 6 factorial, that is equal to 1 times 2 times 3 times 4 times 5 times 6. I'm not sure what that equals to, but that is the total number of possible ways you can order 6 different things. So with that out of the way, let's just start, by figuring out what the question is saying. So we have a 5-digit number, and we subtract a 4-digit number, and it results in the answer 11111. Also, each digit from 1 to 9 must be used. Notice that there's only 9 digits in total in the 4 and 5-digit numbers. So that means that to fulfill that requirement of all the digits being used, each digit must be used exactly once, and also the digit 0 cannot appear anywhere. So what we can do is we can rewrite this expression a little. So we have 1. I'm not going to say the whole number each time, I'm just going to say ones. So we have ones minus the 4-digit number equals to the 5-digit number, and we also have the 5-digit number minus ones is equal to the 4-digit number. So this last expression is the one that I use to figure out the question. And I'm sure there are, many different ways to get to the solution. I'm just going to talk about the one that I used. So also I wrote the expression like this, where the digits line up vertically. So I define the 5-digit number as A, B, C, D, E, the 4-digit number F, G, H, I, though this actually isn't very helpful. You might try to, use variables for each digit, but you'll quickly realize that that doesn't really work, right? You have 9 variables and you can't really work with that easily. So in general, when you have a question like this, the first thing you should do is check the extremes. So let's try the smallest possible 5-digit number and the largest possible 5-digit number. So we use the smallest possible, which based on the rules is 1, 2, 3, 4, 5, right? Because we can't use the same digit again. So 1, 1, 1, 1, 1 would never work for our 5-digit number. So if we do that here, we end up with 1, 2, 3, 4. And then if we use the biggest possible 5-digit number, 98765, we end up with 87654 here. And what you might have noticed that is when our 5-digit number is too big, it is impossible to get a 4-digit number as the result. So like right here, you know, subtracting the ones from this gets us a 5-digit number. And in fact, it's over 80,000, which means it's nowhere even close to being a 4-digit number. So right away, we can see that the 5-digit number must start with a pretty small digit. Clearly, it can start with a 1, right? We just proved right here, if it starts with a 1, we can get a 4-digit number. And so the question is, okay, can it then start with 2? So what we can do is we can check the smallest possible 5-digit number that starts with 2. So let's do that right here. The smallest possible one would be 21345. And if we subtract our ones from it, you see that we get 10234, which is still a 5-digit number. So that means a 5-digit number that starts with 2 is too big. So we have now found out that the first digit of the 5-digit number must be 1, because if the first digit is anything greater than 1, then we cannot actually solve, the equation the way it wants us to. So next, let's look at, one of these again, and it doesn't matter which one we look at. What you'll notice is that we are always subtracting 1 from each digit. And because the digit 0 cannot appear anywhere, that subtraction will always be successful. And what I mean by that is, right, we have these numbers, we're subtracting 1 from them. And because all of these digits have to be at least 1, they cannot be 0, you'll never have to do the thing where, okay, let's say 5 minus 1. Let's say this number was bigger than 5, then what you do is you cross this one out, take one out, put the 10s here. We'll never have to do that, right? Because all of these digits are at least 1 and we're subtracting only 1s from them. So we won't have to do this. And so what that means is that whatever digit we have in our 5-digit number, we cannot also have its adjacent digit, right? Because if we have, so let me erase these blue lines I just added. So we, for example, have 5 right here. We're going to always subtract 1 from it, which means you'll always get 1 digit less. So 5, 1 digit less is 4. If we have 4 right here in our 5-digit number, then we will end up with 3 in our 4-digit number. And so what that means is we cannot have, if we have 5, for example, in our 5-digit number, we can't also have 4, because that 5 in the 5-digit number will turn into a 4 in the 4-digit number. And of course, we established we can only have each digit appear once. So basically what that means, what that means is that our 5-digit number, or sorry, more generally, what this means is that the digits in the 5-digit number cannot be adjacent to each other. So if we have a 1 in our 5-digit number, which we established we must, then we cannot have a 2. If we have, and so actually let me write this out to make it a bit more clear. So we start with a 1, we already established we have to. Because there's already a 1 in our 5-digit number, we can't have a 2, so the next possible digit would be 3. Because we have a 3, we cannot have a 4 in our 5-digit number, so the next one must be 5. We can't have a 6, so it'll be 7, and we can't have an 8, so it'll be 9. And so what you can see here is that our 5-digit number, after starting with 1, must be some combination of 3, 5, 7, and 9, right? We can't, for instance, okay, let's say, so we can't have 2. Let's say we skip 3 and instead we try 4. So if we try 4, we can't have 5, so we do 6. We can't have 7, so we do 8. We can't have 9, but there's nothing left after 9, right? We're not allowed to do 0 because that's not one of the numbers available to us. And so that doesn't work. And so what that means is that our 5-digit number must start with 1 and then be some combination of the digits 3, 5, 7, and 9. And if we, actually complete this subtraction here, what that means is that our 4-digit number must be some combination of 2, 4, 6, and 8. And so we now have, these rules, right? We already found the rule earlier that the 5-digit number has to start with 1. And now we found these rules that our 5-digit number has to then have a combination of 3, 5, 7, 9, and the 4-digit number has to have a combination of 2, 4, 6, and 8. So just in case if you want to check to make sure these rules are working, a good way to do so is to check the limits of these rules. So let's try the smallest possible 5-digit number with our rules, and you'll see how this does work, right? We start 1, 3, 5, 7, 9, we get 2, 4, 6, 8. So we have each digit appearing one time, so this works. And then if we do the biggest possible 5-digit number with our rules, so 19753, you'll see that once again it does work. Each digit only appears once, and there are no zeros in either of these. So it's probably safe to assume that the rules we came up with do work, since we checked the two most extreme values and they worked. So we have a combination of 4 digits. To find all the possibilities, we use a factorial of 4, which equals to 1 times 2 times 3 times 4, which is 24, and that is the answer to this question. And this is, just a probability thing. If you have a certain number of things, and the factorial of that number gives you the number of possible combinations, and that's just something you need to know. If you have time when writing the exam, you can check a few numbers, or I guess in theory even all of the numbers, if you want to make sure this is in fact the correct answer. Of course, you probably won't have the time during the exam. It's pretty, it's only an hour long. There's a lot of questions, so you're pretty limited. But anyways, if you look at this example right here, for instance, 1, 3, 5, 7, 9, you will see that the one in the 5th digit will always become a 0, right? Because we have 1 minus 1. So this will always end up being a 4-digit number based on our rules. And then each of these odd numbers will always get 1 removed from them, resulting in even numbers. So basically, if you look at this, and just think about it logically for a bit, all 24 of our combinations will have a 5-digit number up here and a 4-digit number down here, and each digit from 1 to 9 has to be used exactly once. So you don't actually have to go and check to make sure this is the correct answer. If you just kind of evaluate it for a bit, you can just prove that this will in fact always give us the right answer. And if we use 4 factorial, we can find there are 24 combinations, and so that is the answer to this question. Okay, so next is the section 2 question, which says, draw a circle C on a plane. Put n distinct points on the circumference of C. Join any 2 of the endpoints with a chord. Suppose that no 3 chords intersect at any one point inside C. Let C sub n be the number of such chords, I sub n that of intersections of the chords inside C, and R sub n that of regions in C bounded by an arc and or some chords. Fill in the blanks with the answers to the following questions. So for this question, you need to know the binomial theorem, meaning you need to be able to understand this notation right here, which says n choose k. But to start, I'm just going to show you how to answer the first part of the question, even if you have no idea what this binomial theorem is. In that case, you would still be able to get 15 out of 25 marks for this question. So the question says to draw a circle. And then you need to put n number of points along the circumference of the circle. So, let's just say I'll put 1 here, 1 here, here, so on. Then we'll be joining the points with a chord. So these 2 points, we'll get a chord between them. Same with these 2 points, these 2, and again, so on. And I'll erase these now because I'll be going to depth on what we're doing later, showing an example at the moment. So we need to find the expressions for the number of chords, which is C sub n, the number of intersections of chords, which is I sub n, and the number of regions in the circle, which is R sub n. But the first part of the question only asks us to find the values of these from 1 to 6. So we just need to make 6 points along the circumference, connect them with lines, and just count how many chords, intersections, and regions we have. So let's start with that. And to make it easy to track, I made this table over here. Let me make sure everything is visible. Yeah, like that. So I made that table. So let's start with just 1 point. So ignore those red points. I'm going to restart with these gray points. So we have just 1 point. In this case, the number of chords is 0, since you need at least one other point in order to connect them together and make the chord. The number of intersections is also 0, since of course, in order to even have an intersection, you need at least 2 chords for those chords to intersect each other. So I is 0. And then the number of regions is 1. It says the regions can be bounded by an arc and or chords. So the entire circle is technically one large arc, which means it is one large region. So we have one region when we only have 1 point. So now let's add a second point. So now the number of chords is 1, right? Because we have these 2 points, they make 1 chord. So C sub 2 is 1. The number of intersection of chords is still 0. And now the number of regions is now 2, since this chord split our circle into 2 regions. We have this big region right here, and we also have this smaller region. So now we have 2 regions. So now let's add a third point. So the number of chords is now 3, right? Because this third point connects to the 2 points we had earlier. So C sub 3 is equal to 3. And the number of intersections, clearly still 0. Our chords have not intersected yet. And the number of regions is now 4. And now let's add a fourth point. So now the number of chords will be 6, right? Because this fourth point makes chords to all 3 of the previous points. And you'll notice that in general, the number of chords added is just 1 less than the number of points. So we added a fourth point in this step, which means we had 3 points already there for it to connect to. So we add 3 chords. So now we have a total of 6. And we now finally have an intersection right here. And so our number of intersections is equal to 1. And the number of regions is equal to 8. And an easy way to keep track of the number of regions is to just count how many new regions you create as you draw the lines. So let me, remove one of these lines and I'll draw it again just to sort of show what I mean. Actually, let's not do that line. Sorry, let's remove this line. And so as soon as we start drawing the line and we're going to go from this point to this point, as soon as we start drawing it, we see that we're cutting this region into 2 regions. And so that means we have +1 region already. And then once we intersect this chord, we're now cutting a different region into 2 regions. So that is now +2 regions. And so overall, if you do that plus these other lines, you'll see that we added a total of 4 regions. Also, you might find it hard to keep track of all 3 of these quantities, the chords, the intersections, and the regions at the same time. In fact, I don't think you almost definitely will. So it would definitely be easier to draw 3 circles and do this exercise for each quantity, the chords, the intersections, and the regions separately. So, you draw 1 circle and you just keep track of the number of chords. Then you draw another circle, you just keep track of the number of intersections. And finally, you draw a third circle and you just keep track of the number of regions. But to save time in this video, I'm only going to do it once. But if you do that, this question does actually get quite easy. So anyways, hopefully you get the idea. We're now going to add a 5th point. We're going to draw the chords from that point to all the points you already have. And also, like I said, you would also be keeping track of the number of intersections and regions that you create. Just to save time, I'm not going to go into a lot of depth there. Hopefully you can understand what the point is. But now we have 10 chords, we have 5 intersections, and we have 16 regions. And also, remember that the question says no 3 chords intersect at any point inside C. And what that means, you cannot have a line that looks like this, for example, where it goes through an already existing intersection right here. And that's important because if you did have an intersection like this, then you'll make fewer new regions and fewer new intersection points. So if we drew this line properly instead, if we drew it like this, you'll see that we created a new region right here, right? We split this whole triangle into 2. And we also created 2 new intersection points right there and there. Versus if we had this line go through the already existing intersection point, we would not be splitting this region. And also we wouldn't be making any new intersection points. And so our numbers wouldn't add up. So definitely make sure when you're drawing the lines that you don't have any, intersection points that repeat. And the easiest way to make sure that happens is do not space your points evenly along the circle. If you try to space them evenly, you're very likely to get a shared intersection point. But if you space them in like random distances like I've been doing, then it's a lot less likely to happen. And of course, if you really need to, then you can always just like curve one of your lines. So let's say we have this line going like here. You could always just curve it a little just to make it clear that you don't have a shared intersection. But if you're doing that, make sure that you don't accidentally have a curved line that crosses a different line twice, right? So don't draw a line that looks like, let's say we have it like this and then we curve it back and now it's crossing this line twice. Make sure you don't do that. In general, like I said, easiest way, just don't split your points evenly. And you should hopefully avoid that problem. And so anyways, we have to add one more point. Let's do that one like right here. To do that, we add 5 more chords. So 1, 2, 3, 4, 5. So now our number of chords is 15. And if you keep track to the number of intersection points, that will be 15 as well. And the number of regions is 31. So you might have thought, looking at these numbers, that there's a pattern, that you're just multiplying by 2 every time. But that's not the case. There's actually only 31 at the end. And again, it's hard to keep track of all 3 of these values at once. So definitely would suggest draw 2 or 3 circles and do this process 3 times. And each time only focus on one of the quantities. If you do that, this question really isn't that difficult at all. And with that, you have the answer to the first 3 parts of the question. And that's already worth 15 out of 25 marks. And it didn't really require any specific knowledge. You just had to draw a few diagrams, count some simple numbers, really. And also, of course, understand the question, which, at least in my case at first, I didn't really get what it was asking. The wording's a bit confusing, especially since they don't give you a diagram. You kind of have to figure out what you're drawing on your own. And now, unfortunately, the last part of the question does require some pretty specific knowledge about the binomial theorem. So I will try my best to give a quick explanation of it. But if you want to really properly understand this stuff, you will just have to, I think, read a chapter in a textbook or watch some videos online about what the binomial theorem is. But anyways, I'm going to try to explain it quickly here. So actually first, let's consider this notation right here, which says n choose k. So what this means is if I have n things and I want to choose k of those things, how many different combinations of things can I choose? So for example, let's say we have 3 choose 1. So I have 3 things and I want to choose one of those things. And how many different combinations can I do that? Well, this one's pretty straightforward. There are 3 different ways to choose one thing. So if our 3 things are, thing A, thing B, and thing C, then I can either choose A, B, or C. And so this notation right here, 3 sub 1, this is just equal to 3. Now for another example, let's do 4 choose 2. So now I have 4 things and I want to choose 2 of them. So how many possible combinations are there? Well, let's list our 4 things as A, B, C, and D. And so, possible combinations can be AB, AC, AD, BC, BD, and so on, right? And to be clear, the order of things doesn't matter. So BA is the same as AB, since we still chose the same 2 things. We're not talking about order, we're only talking about what objects or things you choose. And so that's what this notation means. And hopefully you can see how this can get pretty difficult to figure out with brute force once the numbers get pretty big. Like let's say I did, 7 choose 4. You have to manually list out a lot of different combinations to find what this equals to. So instead, what we can do is use this thing right here, which is called Pascal's triangle. So you might already recognize this from binomial expansion, but basically to draw this triangle, you start with just 1 at the top right here. So this 1, we start with just that. And then when drawing the next row, you add the 2 numbers above it. So for the second row, the only number above is again 1. So this is just 1 and 1. For the third row at the very middle, the 2 numbers above it are 1 and 1. So this number adds up to 2. In the third row right here, you have 1 and 2 above it, so that adds up to 3. Here, we have a 6 because the two numbers above it are 3 and 3, and so on. And so what does this triangle do for us? Well, as you can see, I labeled these horizontal and diagonal rows with their corresponding binomials and n values. So to start, let's look at the first diagonal row, which is just n choose 0. So then when n equals to 0, this right here is equal to 1. So 1 choose 0 is equal to 1. Or sorry, 0 choose 0 is equal to 1. And that means if you have 0 things and you're choosing 0 of them, then there's only one possible combination, which is just to choose 0 things. Next, n is equal to 1, which means we have 1 choose 0, and that is still equal to 1. That's because if you have one thing and you want to choose 0 of those things, and the answer is still 1, because there is still only one way to choose 0 things. When n equals to 2, then 2 choose 0 is still equal to 1, and same when n equals to 3, 4, and so on. Basically, it doesn't matter how many things you have. If you need to choose 0 of those things, then there's only one possible way to do it. Next, let's consider n choose 1. So if this n is equal to 1, then you have 1 choose 1, and that clearly equals to 1. If you have one thing and you're picking out one thing, then there's only one way to do it. Then let's look at 2 choose 1. We have two things and we're picking out one of them. Therefore, there are two possible options. Either you pick the first thing or the second thing. So this continues as n increases. N choose 1 is just equal to n. Also, you may have noticed that in the triangle there is no value for 0 choose 1. And well, actually there is a value, but it's just equal to 0. And this makes sense if you think about it. 0 choose 1 means you have 0 things and you want to pick one of those things. But if you have 0 things, then how will you pick out one of them? It's not possible to do that. So that means that there are 0 possible ways of picking one thing out of 0 things. So the answer to 0 choose 1 is just 0, and that's why we don't bother writing it in the triangle. For n choose 2, the idea is the same. If you have 0 things, you can't choose 2 of them. So the answer is still 0 when n is equal to 0. And if n equals to 1, meaning you have one thing, there's no way to pick 2 things out. You can't pick out 2 things when you only have one thing to choose from. So 1 choose 2 is still just equal to 0, and that's why we don't draw it in our triangle. And that idea continues for all of these. N choose 3, n choose 4, and so on. And the question even says this, right? At the very end, it says, for binomial coefficients m choose k, note that m choose k is equal to 0 if m is less than k. But hopefully my explanation makes sense for why it equals to 0. So now let's actually try to find the binomial coefficients for c sub n, I sub n, and r sub n. Let's start with the first one, which is c sub n. So we already found the first 6 values for c. They are 0, 1, 3, 6, 10, and 15. And what you notice is if we look at our triangle, that the row for n choose 2 actually fits perfectly. So c sub 1 means that n equals to 1, and 1 choose 2 equals to 0, as we discussed. Then when n is equal to 2, n choose 2 equals to 1, which we have right here. When n equals to 3, this is 3, which is the same as c sub 3. When n is 4, this is 6, which is the same as c sub 4, and so on. And it matches all the way to n equals to 6. So we can say that c sub n is equal to n choose 2. And so that is the answer to one of these questions. For I sub n, it's the same thing. If you look at a pyramid, you see that n choose 4 is equivalent. When n is equal to 1, 2, or 3, n choose 4 is equal to 0, which is the same as our values for I sub 1, 2, and 3. Then it equals to 1, 5, and 15, which again is the same as what we found earlier when we just found the I sub 4, I sub 5, and I sub 6. And that is, of course, so yeah, that's the same as n choose 4, which means that the answer for I sub n is n choose 4. Finally, we have r sub n. And in this case, unfortunately, there is no binomial coefficient that matches it perfectly. Because our values for I sub n start with 1, 2, and 4. And if we look at our triangle, the only one that starts with 1, 2, then has 3. So clearly it's not the same, right? This is 1, 2, 3, and we need 1, 2, 4. So for r sub n, what we have to do is use a combination of binomial coefficients. And to find that, we're going to have to just use some problem solving. So firstly, we know that the circle starts with one region, right? And that's just the entire circle itself. Next, whenever we add a new chord, that chord will divide the regions that it goes through into two. So let's look at the circle here, and let's just add in a chord. So a chord like that. Clearly, it has divided this one region that it passes through into two regions. So put another way, every chord added adds one new region for each region that it passes through. So for this first chord, it only passes through one region, meaning it only added one new region. Now, let's add a second chord. It'll go something like that. So this time, it passes through the first region here, and then after it intersects with the first chord, it passes through a second region. So it has added two new regions this time. Let's add one more chord and see what happens. So as we start drawing it, immediately, as soon as we start drawing the chord, we are already passing through a region. And clearly this is always the case. When you start drawing a chord, you are immediately passing through a region in our circle. So logically, we can say that each new chord always adds this first new region. Then look what happens when we pass through this other chord. So we have now made a new intersection. And now that we have made that new intersection, we are in a new region. That means that we are splitting this new region into two. So logically, what that means is that creating a new intersection directly correlates to adding a new region. So what we can say is that for every new chord added, the number of regions added is 1 plus the number of new intersections it creates. So, right here we made one new intersection and that added another new region. Then as we continue, we have now made a second new intersection and that has once again created another new region. So if we put all of this together, we can say that R sub n is equal to 1, which is just the initial region of the circle itself, plus the number of chords, since each chord drawn adds one new intersection right away, plus the number of intersections, since each new intersection also adds one new region. And here's the thing, we already found the number of chords and the number of intersections in terms of n, right? That was the last part of the question. We just did that when we found sub n, or C sub n and I sub n. So to find R sub n, we just need to add 1 plus C sub n plus I sub n, which is equal to 1 plus n choose 2 plus n choose 4. And that is the final answer to this question. So hopefully that's helpful if you never learned about the binomial theorem before, which was the case for me. It does seem like the binomial theorem is a regular part of the Japanese curriculum since there are a few questions that use it across the practice exams. So if you have time before your exam, then it might be a good idea to spend a little while learning it from a textbook or something. But it doesn't show up on every exam, so you might also be able to risk not studying it, but that's up for you to decide if you want to take that risk or not. Okay, so finally we have the section 3 question, which says, let C be the plane curve y equals to f of x defined by the cubic function f of x is equal to x cubed minus 4x squared plus ax plus b, where a and b are real constants. Fill in the blanks with the answers to the following questions. When C is tangent to the x-axis at x equals to 3, what are a and b? So to answer this question, you need to be familiar with basic derivatives and integrals, specifically using the power rule. So to start, we need to find the values of a and b. We initially only have one equation and two unknowns. But if we find the derivative of our equation, then we now have two equations with two unknowns. So we start by doing that. F prime of x, meaning the derivative of f of x, can be found with just the power rule. Now the question tells us that our curve C is tangent to the x-axis when x equals to b. What that means is that x equals to 3. And what that means is that x equals to 3, f of x must equal to 0, since our curve is tangent to the x-axis. And for that to be the case, it must be touching the x-axis. Also, at that exact point, at x equals to 3, our curve must be parallel to the x-axis. So our curve might look something like this. Now, I don't know exactly what the rest of the curve looks like, but right now the only part that we really care about is where x equals to 3. At that point, our function just touches the x-axis, so it might look something like this. And so what that means is that at x equals to 3, the derivative of our function must equal to 0. So because the derivative gives us the slope of the tangent line at that point, and because our curve is tangent to the x-axis, which is horizontal, our slope must be 0. So we plug x equals to 3 into our equation of the derivative, and the equation equals to 0. And so when we arrange, we find that a is equal to -3, so that is the first part of our answer. Now, we can take the value of a and plug it back into the equation of our function. So, and also, we know that at x equals to 3, our function must equal to 0, since our curve has to be touching the x-axis at x equals to 3. So similar to before, we can plug x equals to 3 to the equation and make it equal to 0. Then, when we rearrange for b, we find that b equals to 18, and that is the second part of the answer. So next, the question asks, when 1 holds, meaning the question that we just answered, or the part of the question, we just answered part 1. So when that holds, find all x such that c has points in common with the x-axis. So what that is saying is we just need to find all of the x-intercepts of our curve. So right now we have this function, f of x, which is cubic. So to find the x-intercepts, we need to do a bit of factoring. To start, we already know that one of the x-intercepts is at x equals to 3. What that means is that x minus 3 is a factor of our function, since when x equals to 3, x minus 3 equals to 0. And we know that our function equals to 0 at x equals to 3. So we need to factor out x minus 3 from our function. So to do this, I chose to use long division. I don't know, if you don't know how to do this, you can pretty quickly learn if you search up long division with polynomials on YouTube. There's a lot of helpful videos, it's pretty straightforward, and I will link the video that I used to learn this in the description. There are other ways of factoring a polynomial, but I personally find this method to be the easiest. So once you do the long division, you'll find that our function equals to x minus 3 times x squared minus 1x minus 6. So now we have a quadratic, which you should hopefully already know how to factor. And so once we do that, we find that that quadratic part equals to x minus 3 times x plus 2, which means that we have the x-intercepts 3 and -2. Now we already have the x-intercept 3 from before, so that means the only answers to this question are x equals to 3 and x equals to 2. And so those are the answers to the second part of the question. Now last is part 3, which reads, when 1 holds, calculate the area S of the limited region bounded by C and the x-axis. So we need to find the area of this limited region. To start, we need to know what exactly this limited region is. So the easiest way to do that is probably to figure out what our function looks like and see this limited region. So since we know that our function touches the x-axis at x equals to 3 and x equals to -2, let's check the value of the function at in between x values. Also, because we have x minus 3 in our factored function twice, it just becomes x minus 3 squared. So let's first check what our function is like when x is less than -2. So I chose -3, and if you plug that in, you get -6 squared times -1. And something you'll realize is that since this term right here is squared, right, we have x minus 3 squared, it will always be positive. So we just need to look at the other term to determine if our function is positive or negative. So -3 plus 2 is still negative. So this term is negative, which means our function is negative when x is less than -2. Then let's check between -2 and 0 by setting x equals to 0. Sorry, let's check between -2 and 3 by setting x equals to 0. 0 plus 2 is 2, which is positive, and so our function is positive. Finally, let's check when x is greater than 3 by setting x equals to 4. And once again, our function is positive. So we can draw an idea of what our function looks like. And it's something like this. So when x is less than -2, it's negative. And then when x is between 2 and 3, it's positive. It touches the x-axis at -2 and at 3. So our limited region is this shaded part right here, which is the area under the function between -2 and 3. So that means we need to take an integral of our function from 3 to -2. Now this is just a simple power rule, so I won't be going over all of the steps. Just make sure that you're being very careful when answering a question like this. Since you don't have a calculator, it's really easy to make a typo somewhere along your steps if you're not careful, and then your final answer will be wrong. And as far as I'm aware, for these exams, they only look at your final answer. So even if you had the right idea and you did everything right and you just happened to make a typo, you'll get no marks for this part of the question. But anyways, after simplifying all of this and combining all the terms into one, we end up with this, which is that the area is 625 over 12, and that is the final answer to this question. So that is it for this exam. I hope you found this video helpful. If you have any questions about this exam, leave a comment and I will try to help you if I can. And if you're writing the MEXT exam soon, then good luck and have a good day.